Well, if you have a printer and you have enough time, maybe you can find a copy of the AP exam problem from the Level C exam, the year 2009, problem number 2. If you have it printed out, then you can work out the solution alongside with me from this video lecture. Go ahead and hit pause if you need to, and you can resume once you have a printed copy. Okay, so here we go. The problem describes a long, thin, rectangular bar as pictured here. The mass is known, and the length is known. What we don't know is how the mass is distributed. We're told, and this is the key, that it's a non-uniform distribution of mass. So its center of mass does not lie at its geometric center. However, the position of this center of mass is located at a known distance of x, and x has been labeled in this diagram. So the problem at hand is to determine what's the rotational inertia of the bar, what's the also known as the moment of inertia of the bar. So you suspend it from the very top, and that forms an axis of rotation, and we have to figure out experimentally as well as theoretically how we could get a value of this rotational inertia. So let's get into the theoretical determination. So we can apply an equation of motion and express a differential equation that describes the angle that the bar makes with the vertical. So we're going to pull the bar back so it sits in this position. That's the farthest angle that will pull it back. That's theta max. So when we release it, at some instant in time, it's going to be part way back to vertical. So we can draw the bar in orange in that position. And if I copy that drawing, we get something like this. The axis of rotation is at the very top, and then there's a force of gravity pulling straight down, acting at the center of mass. So that's mg, and then the distance to that center of mass is a distance of x, as described in this problem. So the differential equation follows from Newton's second law for rotation. That's the one that tells us that the net torque is equal to the rotational inertia times angular acceleration. Well, the net torque in this case is the cross product between the force of gravity and the lever arm. Now that lever arm of x points from the axis of rotation to the point where the gravity force is applied, but if we extend that lever arm, then it makes the same angle with theta that the rod does with vertical. So net torque in magnitude is nothing more than mg times x times sine theta. And that's equal to I times the second derivative of theta with respect to time. Let's see, now we're told to apply a small angle approximation in our solution. We don't actually have to solve the differential equation yet, we just need to state it. So let's clean up our act a little bit here and simplify this expression. We have the second derivative of angle with respect to time is equal to mgx over I times sine theta. Now I'm actually missing something. I believe this should be a negative mgx sine theta, and that's due to the idea that the torque is restoring. If you pull the rod with an angle in the clockwise direction, then the torque that pulls it back to vertical is applied in the counterclockwise direction. So because the opposite nature of these vectors of theta compared to alpha, then that leads to the minus sign in this equation. So that's all we need to do to write a differential equation. Now we have to apply the small angle approximation so that we can solve this differential equation. The small angle approximation just tells us that sine theta is pretty much the same thing as theta as long as the value of theta is small and, more importantly, expressed in radians. So the second derivative of theta with respect to time is negative mgx over I times theta itself, which means we're at a point in our derivation where we have to make a guess. The best guess you can get now by practice and intuition. You've seen time and time again how sinusoidal functions, when taken the second derivative of a sinusoidal function, you get back the same sinusoidal function with a negative constant spit out. So if we make a guess that the angle is equal to whatever maximum angle you set by pulling it back to this position, the angle at any instant in time equals the maximum angle times cosine of omega t. So there's our guess. Now let's see if it's correct. We'll take the first derivative. This would give us negative omega theta times sine omega t. And then the second derivative gives us negative omega squared theta max cosine omega t. So there it is. We've got a negative constant times our original function theta. So this all works out provided that omega squared and mgx over I are one and the same. So from that, we can determine that I must be equal to mgx divided by omega squared. Describe our experimental procedure that we could use making any additional measurements so that we can experimentally determine what the rotational inertia of the bar should be. So in theory, it should be this value. In practice, we need to come up with a way to collect data so that we can measure any additional quantities. Now, we were already told from the outset, we've already made measurements and we know the mass of the rod, and we even know the distance x to the center of mass. We can take g, assumed to be 9.8 meters per second squared. So we already know the mass, we already know the value of x, and we know g. We need to come up with some experimental way to get the value of omega. Perhaps the best way to do it would be to experimentally get a value for the period. Now, we know that period is equal to the inverse of frequency, and we know that frequency is equal to omega divided by 2 pi. So, in other words, period is 2 pi divided by omega, or omega is 2 pi divided by the period. Now, you could grab a stopwatch, pull it back to some small angle, release it, and by the time it comes back to you once, stop the stopwatch and you would have measured the period. The problem is we have a fair amount of error in starting and stopping our stopwatches. Either we have delayed reaction time or we have anticipation, and so our timing can go long or run short. So to eliminate any of those random errors in timing, a good idea would be to time the swinging of the rod for 10 cycles, and then if you divide the time for 10 cycles by 10, that will give you the period. So that would be perhaps the best experimental approach. Measure the time it takes for 10 swings and divide it by 10. By doing so, you'll have a value of the period. If you take 2 pi divided by that experimental value for the period, then you have a value for omega. And once you have a value for omega, you can plug it in to this formula and determine the value. Part C, suppose that we weren't given the location of the center of mass. So this is no longer a question about simple harmonic motion. I think this AP problem up to Part B challenges your understanding of simple harmonic motion and the behavior of the physical pendulum. Part C is about methods for finding center of mass. So describe an experimental procedure that you could use to figure out the center of mass if you didn't already know it. If you're not familiar with this one, I recommend you try it. If you have a yardstick, I want you to do an experiment with a yardstick or a meter stick. Take a finger of your left hand and put it somewhere near one end of the meter stick, and with your right hand, take your other index finger and put it near the right end, and then slowly bring both hands together. Now, there's no guarantee that they move at the same rate. However, no matter how you do this, whether you move your hands fairly slowly or a little faster, they'll always end up meeting at the center of mass. And because we know the center of mass of a meter stick should be right at the 50 centimeter mark, or of a yardstick should be right at the 1.5 foot mark if 1 yard is indeed equal to 3 feet, then you can verify that this method is correct. Now you can use it to take anything that's non-uniform and try the same approach. So if you have a baseball bat, for example, you can try this same experimental approach. Take your left hand and put your finger near the left end with the index finger of your right hand somewhere on the right end, and start to bring your fingers together. They should meet not in the geometric center, but they should meet at the center of mass. Another object you can try this with is a broom. See if you can find the center of mass. It's not at the geometric center. It's somewhere closer to the head of the broom. So that's what I offer to you. If you're curious why this works, you might want to try investigating and doing your own research on the madness behind this method.